So what that looks like, we'll be factoring things like x squared minus x minus 6. In order to factor something like that, we're going to get two groups of two terms. The first two terms, or the first term in each group, is an x. The second term, what has to happen with the second term in each group? They have to multiply to give us -6. They have to add to give us -1. So we're searching for a pair of numbers, multiply to -6 and add to -1. So some options we have to multiply to -6, -1 and 6. 1 with -6, -2 with 3, 2 with -3. We need to pick the pair of these that if we add them, we get -1 back. The pair that does that is 2 and -3, so this factors into x plus 2, x minus 3. Right, and we'll spend some time practicing with that. But that's kind of the basic factoring technique for when we have a leading coefficient of 1. The leading coefficient is the coefficient for the squared term. So when that leading coefficient is 1, this is one of the approaches we can use. Questions about that? Remember that from 171, maybe, hopefully. If not, I'm not remembering it yet. Hopefully some of it will come back a little quicker. So here's a new one we can try. Same idea, right? A couple things to identify, really one thing to identify, just that the leading coefficient is 1 and we have 3 terms. We have a leading coefficient of 1 with 3 terms. We're going to factor the same way we did above. First term in each group is always going to be x. Then we need to find a pair of numbers that multiply to -21 and that add to +4. So again, if you spot those two numbers right away, then that's cool. No need to kind of go through this listing process that I'm about to do. But if you don't spot the numbers, you can certainly come over here and make a list. 1 with 21, 3 with 7. Those are our only two options. Since we need it to be -21, then one number in each group would have to be negative. So maybe -1 with 21, -3 with 7, or 1 with -21. 3 with -7. The pair that adds to +4 is -3 with, the pair that adds to +4 is -3 with +7. Questions about how we factored it? If we're talking about an equation, then what we would do once we have these factors is to set each one of them equal to 0 and solve for x. So x minus 3 equals 0 tells us x equals 3. X plus 7 equals 0 tells us x equals -7. My bigger focus is just factoring, period. But again, if you're solving an equation, you would just take each factor once you get it and set those equal to 0. Questions about that second one? If not, here's a third one for you to try. Give you a minute to try this one on your own. Same approach. The leading coefficient is still 1. We still have 3 terms. So see if you can factor that one. Again, this is our third one of these. So the first term in each group is an x. We need some numbers that multiply to 54 and add to negative 15. So again, we can make our list. Since they need to multiply to a positive number, but add to a negative number, that tells us that each number with the factors, each factor has to be negative. So -1 with -54, -2 with -27, -3, is that going to work? -3 with 18, 4's out, 5's out, 6, -6 with a -9, 7 and 8. I think that's it. So these are our options. We need something that adds to -15. So that's going to be x minus 6, x minus 9. Again, if we're actually interested in solving the equation, my point is to factor, but if we want to solve it, set each one of these equal to 0. That tells us x is 6 or x is 9. Questions about that one? Okay. So we're going to take a step back, actually. Let's say we need to factor something like this. So 4x to the 5th plus 12x minus 8. So we like to factor things that are quadratic. This isn't, right? Our degree is 5 there. So we're not going to go through the same approach we were using for the previous one, but one thing to always be on the lookout for is a common factor. And so here we have a common factor of 4. So what we can do is factor out a 4 from each of these terms. And that's really it. If this part in the parentheses can be factored further, you certainly could do that. But in this case, right, it doesn't factor anymore. So we just take out the common factor and then we kind of move on. This one wouldn't be, it's not all that interesting since it doesn't factor additionally, but sometimes the greatest common factor is all we can do. Let's try one like that. So the square root of 3 times x squared plus 3x. So here, what we've got is, so a couple of different ways to approach this one. We certainly have a common factor of x. Let's just consider that one for the moment. If we take out the common factor of x, we're left with the square root of 3 times x plus 3. But there's, depending on how interested you are or how much you notice this sort of thing, you can actually take out a common factor of the square root of 3 as well. So we can remove a square root of 3 times x from each term. For the first term, that would leave us just with an x. for the second term, it would leave us with a square root of 3. So both of these are totally fine. There's a question in the lab manual that's kind of similar to this. And of course, anytime you're factoring anything, the way you can check it is to multiply back the things you just wrote as your factors, right? So if we distribute the square root of 3 times x to both of these terms, we get back the previous row. We distribute the x to each of these terms, we get back the previous row. So as long as that's true, then how you factored is okay. Let's try one more of those. So a little more interesting here, I guess. Have a shot at factoring the greatest common factor on the left side of this equation. See what you can come up with for that. Okay, so when you're looking for a GCF, especially when there's multiple parts of this to consider, what I would do is just look at uh, each of these components separately. So the coefficients, we'll look at those. That'll be the numbers here. So between 16, 4, and 10, what we're looking for is the greatest factor we can remove from all of those numbers. In this case, that number is a 2, or that factor is a 2. Then we can look at the a's. We have an a to the third, an a squared, and then just an a. What that tells us is that we can remove just an a. We can remove an a with the smallest exponent from our option. So we have an exponent of 3, of 2, and then of 1. So we can remove a to the first power. From the b's, we have a b squared, a b, and a b. We can remove the b raised to the smallest of those powers, 2, 1, and 1. We can remove a 1. So what that leaves us with, 16 divided by 2 is 8. A to the third, when we take out 1a, that leaves us with with a squared. B squared, when we take out 1b, that leaves us with b. 4, when we take out the 2, that leaves us with a 2. A squared, when we take out an a, that leaves us with a. B, when we take out the b, leaves us with 1, which technically we don't need to write that, so we'll just leave it as 2a. 10, when we factor out the 2, we get a 5. A, when we factor out the a, it's a 1. B, when we factor out the b, it's a 1 as well. So really there we just get a 5. So our factored version is 2ab times 8a squared b plus 2a plus 5. Recognizing the common factors is certainly something to be able to do. Often that's going to be your first step in factoring. That's not where we started because I just didn't. I don't really have a great reason for why. But starting with the common factor is what you should check first. After that, see what other ways you can factor from what you're left with. Questions there. Okay. Factoring by grouping, we're going to mention that briefly, and then we're going to actually use that as part of a larger process we'll look at next. So factoring by grouping, you would suspect to factor by grouping, or you would suspect to check that if you're trying to factor something with 4 terms. So we can't factor using the first approach we looked at today because we don't have 3 terms, right? That first approach only works if there's 3 terms. We could check for a common factor. We should check for a common factor, but there isn't one. So we'll move past that. But certainly notice that there are 4 terms. And so maybe we can factor this by grouping. How that works is we look at the group of the first 2 terms that I've outlined in blue, parentheses, the next 2 terms that I've outlined in red. And we're going to take out the greatest common factor from each group. So the blue group, we have a common factor of x squared. In the parentheses, that leaves us with x plus 3. In the red group, we have a common factor of -4. That leaves us with x plus 3 in the parentheses there. Once we've done that, once we've removed the common factor from each group, if the insides of these parentheses match, we can take this one step further, right? That x plus 3 is actually a common factor between these 2 terms. We have 1 term in blue, 1 term in red. They each share a common factor of x plus 3. So we can actually factor that x plus 3 out, which leaves us with x squared minus 4. Questions there. So that's the factoring by grouping part. We actually can factor this further because x squared minus 4, thinking back to your 171 days, x squared minus 4 is the difference of 2 squares. It factors into x plus 2 times x minus 2. So this is fully factored in. Again, if we're interested in solving the equation, what we would do is take each factor and set it equal to 0 to get x equals -3, x equals -2, and x equals 2. So our factors are here. If we were solving it, those answers are here. Questions about grouping? Okay. So we actually can use grouping as part of a larger method for factoring, and that's called the AC method. We would use this method if the leading coefficient is not 1. So again, our first approach for the day was when the leading coefficient is 1, we can factor using that process. If the leading coefficient is not 1, we likely want to use some other approach. Guessing and checking is an option. That's actually, I didn't know the AC method existed until I was in graduate school. Somehow I had missed it all of my life, I guess. I don't know if it just was never taught to me or what, but I'd never heard of the AC method, and I was super shocked when I saw it for the first time because I hate guessing and checking. I just don't like that. It seems like it could be a pretty big waste of time, you know, when you're actually trying to apply it when time is a concern. But the AC method certainly gives you a clear process to follow from beginning to end and actually results with the correct factoring of this original equation or the original expression. So how the AC method works, A and C, they're talking about these coefficients. A, B, and C refer to the coefficients. So what we do is multiply A times C to get, in our case, -6. And then we look for factors of -6 that add to this middle coefficient, B. So factors of -6 are 1 with -6, -1 with 6, 2 with -3, -2 with 3. Those are our options. The pair of those that adds to -5 is the first one. And so what we do is we separate that B term into 1x minus 6x. So we're not changing the question. We're just making it look different, right? If we combine those like terms, certainly we're going to get back -5x. That's clear. So we haven't changed anything. It's still the same equation. It just looks a little different. But why we want it to look a little different is because now we have 4 terms and we can factor by grouping. So from that green group, we have a common factor of x. From the red group, we have a common factor of -3. Since the insides of these parentheses match, we can remove that common factor. We get 2x plus 1 times x minus 3. Again, to solve, we would get -1/2 or 3. And my bigger point is the factoring, though. Questions about that one? And again, that's called the AC method. Maybe you've seen it before. Some of you indicated that you were comfortable factoring things when the leading coefficient is not one. The AC method is one of those ways. You certainly don't have to use the AC method. If you have some other approach, that's totally fine as well. But here's a new one. I'll give you a minute or two to try using the AC method here. See if you can get this one to factor that way. Of course, if you get stuck on something and just want to chat, let me know, ask out loud, say something out loud or into the chat. But otherwise, I'll give you a minute or so or two to try factoring this one. Okay, so let's try this one. A times C, that's going to give us 24. We need to find a pair of numbers that multiply to 24 and add to -14. So to multiply to a positive number but add to a negative number, that means both numbers are going to be negative. So these are our options. The pair that adds to -14 is -2 with -12. So what we'll do is separate that -14x into -2x minus 12x. Plus. We're going to keep the first term and the last term the same, and then we'll use grouping to complete this, to wrap it up. But again, just to point out, we're not changing the question. -2x minus 12x certainly is still -14x. So the exact same equation still exists now that we started with. It just looks a little different. So from our green group, we can remove a common factor of x. From our red group, we can remove a common factor of -4. Hopefully at this point, what's in the parentheses matches. It should, in order for us to continue using grouping. These should match, but they are actually the common factor now between the two terms. So this factors into 3x minus 2 times x minus 4. To solve, we'd set them equal to 0. That would give us x equals 2/3 and x equals 4. But the factoring is there. Questions about that one? Okay. So here's one more. I'll give you a minute or two to try that one, and then we will chat about it and move on to our last factoring idea. This one's kind of a trick question. Not intended to trick you, but just to point something out. So if you notice there's a common factor of 2, and if you remove that common factor at this point, the leading coefficient is 1, so we can actually factor this using the approach from earlier. The 2 has to come down. We can't get rid of that. But what we're looking for to factor the part in the parentheses here, we need two numbers that multiply to 1 and add to -2. Those two numbers are -1 and -1. So we're not actually using the AC method there solely because the leading code. If you take out the common factor, you don't need to use the AC method. If you wanted to get the solution to the equation, x equals 1 and x equals 1. Questions about that one? Okay. Our last idea we're going to look at then is called substitution. And when you might consider using substitution is when you're factoring something that doesn't look like something you've previously factored. If that, maybe that's a good way to describe that. So we haven't factored anything that has an exponent of 4. But we could use a substitution. We can say, hey, why don't we're going to make the substitution instead of x is, let's use an a, but let's let a equal x squared. The reason I'm picking that is because then we can write this equation as a squared minus 1 equals 0. The substitution that I'm making here is always going to be half. That a is always going to equal x raised to half of the original exponent. And that's so that when we write it after making that substitution, we get something quadratic because we factored quadratic things. That's what we factored the most. We'll look at one in a second and I can emphasize that again. But take this exponent and half it, and then write it I'm using A. You can use any number, any letter. It doesn't matter what you don't use X, but you could use anything other than that. Half that exponent, and then that'll tell you your substitution. So we can factor a squared minus 1. It's the difference of two squares. It's a plus 1 times a minus 1. So we factored it now, but remember, so the question would have been to solve this equation for X. We can solve for A. Right, we can solve for A using our substitution there in blue. And if you ever use substitution to solve these equations, make sure at some point, you must undo your substitution. So we've solved for A, but really we need to solve for X. And so what we can do is undo that substitution by writing, instead of A, we can write X squared equals -1 and X squared equals +1. So I've done all this work in blue to emphasize that it's not what we're trying to solve, it's just kind of part of the process. What's in white is what we need to solve. So X squared equals -1. We can square root both sides to get X equals plus or minus I. X squared equals 1. We can square root everything to get X equals plus or minus 1. Questions about the substitution idea? And there's no obligation to use this. So when you might use this is when you're trying to factor something like sine squared x minus sine x minus 6 is 0. Right? If you don't want to factor things that look like that, what you could do instead is make a substitution. You can let a equal sine x, and then you would be factoring something like a squared minus a minus 6. And this is exactly what we factored earlier today. It factors into a minus 3 times a, at least I think this is the one we factored. This one factors into a minus 3 times a plus 2, which tells us a equals 3 or a equals -2. That in turn tells us that sine x equals 3 or sine x equals -2. So if you're trying to solve trig equations and the trig portion of that makes it appear a little tricky, you can remove the trig portion by using a substitution kind of like this, and then maybe solve something a little simpler. But then just make sure to replace the trig component of the equation before you're finished, and actually solve for x after that. So we're not solving this for x. Actually, if we did, we would get no solution for both of these, in fact. My point isn't though solving the trig equation. My point is just that substitution could be useful in helping you factor these trig equations. But questions about the one we did above, or questions about maybe why you may consider using substitution, or a scenario that you could use it in. Okay. Then here's a new one. I'm going to give you some time to try it, minus 10x squared. What I'll do, though, is point out the substitution we need to make is to let a equal x squared. Again, taking that exponent and halving it. If you want to have a shot at rewriting this, I'll let you rewrite it. I won't do that yet. But rewrite it using the a's, factor it using the a's, and then undo the substitution to get x back in there. See if you can solve for x that way. Yeah, so the question would, I mean, these particular ones would say solve for x. Yeah. So our substitution here ends up giving us the blue equation we get is a squared minus 10a plus 16. We can find two numbers that multiply to positive 16 and add to negative 10. That's negative 8 and negative 2. Which tells us, right? So we factored using substitution. Maybe that makes it easier. Maybe it doesn't make it easier. I don't, that's up to you. The point my bigger goal is to just give you an option to use in the event you want to use a substitution. But we get a equals 8 and a equals 2, which now undoing our substitution tells us x squared equals 8 and x squared equals 2. And so we can solve for x by square rooting everything. X equals plus or minus the square root of 8 and plus or minus the square root of 2. By the square root of 8, of course, if you simplify that, it's 2 times the square root of 2. Questions there? Not, let's do one more of these. X to the 6 minus 3x to the third plus 2. I'm going to leave that one for you to do from beginning to end. Come up with a substitution that you can use. Make the substitution solve for a or whatever other letter you use, and then undo that substitution to solve for x. No, so you cannot um no, they're definitely not equal to 1. I mean, x is certainly not equal to 1, but in the previous example, x is equal to the square root of 2 and to 2 times the square root of 2, so certainly not equal to 1. But the equation from the previous one, I'll just copy it down here. The previous equation was x to the 4th minus 10x squared plus 16 is 0. You need to use some other letter. We certainly couldn't just make a substitution and write x squared minus 10x plus 16, right? If you're going to make a substitution, you've got to pick something other than x because x is already taken. X is already spoken for. Literally any other letter will be fine for your substitution. It just can't be x because this is the original equation. And if you change it to this, you're technically, now this is wrong, right? X can't be equal to something in this top equation, and then you miraculously say x is equal to something else below it. Does that make sense what I'm saying? So, I mean, the coefficient for each of those is 1 for sure. I don't know if I'm understanding what you're saying now. I mean, the coefficient for them is certainly 1. I agree with that. Oh, I see. Okay. So let's try this one. We need to make a substitution. A equals x raised to some power. The power we need is half of that, the largest power from the original equation. That means half of 6 is 3. So our new equation is still going to be x squared. In this case, it's going to be x squared minus 3. Sorry, not x. A squared minus 3a plus 2. We need two numbers that multiply to 2 and that add to -3. That means -2 and -1. And that tells us that a equals 2 and a equals 1. But we don't need to solve for a, we need to solve for x. So we have to undo our substitution. X cubed equals 2, x cubed equals 1. And that tells us x is the cube root of, of 2 and the cube root of 1, which is 1. Questions about that one? Okay. So this is kind of a factoring boot camp. That's more, I guess, if we were titling these individually, that's what we could have called this one. I just sent the second of our surveys. As always, I sincerely appreciate you taking the time to complete these. It is important. It is valuable. I don't ever want you to think that it's just some random thing that I ask you to do for no reason. But that's we're about 5 minutes ahead of schedule. So that means I have about 35 minutes of time for you to ask any questions about anything you've got going on. Questions from identities, WebAssign, lab manual, class examples, the same thing I say each week. Whatever questions you want to talk about, let's do it. You can put them in the chat. You can ask them out loud. Whenever you're ready to go, of course, feel free to do that. Please complete my survey before you leave. Appreciate those of you who already did it just now. To stay as long as you want, leave when you get ready. But whatever questions you have, let me know.
I do have a question, but I don't really know how to ask it. I guess it was from one of our WebAssign practices.
Okay.
But the problem is working with cosine and sine, and it's the sine of x times the cosine of 11x minus cosine of x times the sine of 11x. We have to match that with the formula identity.
Yeah. So this is, I'm going to send a screenshot in the chat in just a second. I think I'm going to try. So this is actually one of the sum and difference identities. But so what's kind of different about this one is we're starting on the right-hand side of the identity. Right? What we've got here matches the right side, and we're going to replace it with the left side. So can you find, do you see the picture I sent? Did it come over?
Yes.
So open that up and look on the right side of those equations and find the one that matches sine cosine minus cosine sine.
Looks like sine times A minus B.
Yeah, so this whole thing is equal to the sine of x minus 11x, which is the sine of negative 10x.
Oh, okay.
So usually we're starting on the left side of an identity and replacing with the right side. It certainly doesn't have to be that way. This case is an example where it doesn't. We start on the right side and end up switching it with the left side or replacing it with the left side.
Yeah, I think I was looking at the product to sum identities and like was confusing it a little bit with like the 1/2 formula ones.
You definitely could use a product to sum.
Okay.
That's just not as quick.
Okay.
The point isn't to be quick per se, right? I mean, there's frequently multiple options, multiple identities you can use. But this sum, and noticing that it's the right-hand side of that sum formula, or sorry, that difference formula is a fair bit quicker. So if you wanted to use the product to sum, you're going to do a product with this group and a product with that group. And then half of your terms are going to end up canceling when you combine them.
Mm-hmm.
And you're still going to be left with the sine of negative 10x at the end of it, which is totally fine.
Okay, yeah, it definitely took me a longer like to get through it. But that okay. Yeah, that makes
So
sense.
did you
Thank
get
you.
you? So you got this answer?
I
Or no?
did using the
Oh, gotcha.
like the product to sum identity and but I just wasn't sure if I did it right.
No, I mean, if you got sine of negative 10x, that's fine. You didn't do it wrong.
Okay, awesome. Thank you.
You're welcome.